Building on the idea of correlations, if R is statistically significant, then a regression line, a best fit line or trend line from our scatter plots, that can be used to make predictions regarding the data. A regression line is called the line of best fit. There is only one regression line for any data set. So y hat would be the value, b sub 0, called b naught, is your y-intercept. b1, that's the coefficient or slope of the variable. You've probably seen this before in one of these forms. Most commonly seen, mx plus b. A couple of key things to remember before you get started in regression. You should not make a prediction with the regression model if the correlation is not statistically significant, if you're using a value outside the range. In other words, your data line only goes so far. Up here would not be a good prediction. Or if the population is different from that of the sample data. So here's a quick example about age and reading level. If we plug the data into Excel and determine the scatter plot, click on Insert to get the scatter plot, and in Chart Tools on Format, then Trend Line to see your regression line, which is what we're studying. Going through Excel, Data, Data Analysis, and Regression, you get this type of printout. Notice you have a R value, 0.988. That would be a very strong positive relationship. But you're also given an R square value. In this scenario, R squared, or coefficient of determination, would say that 98% of reading level, Y, is explained by age, X. Looking at another part of our printout, we're going to look for, not looking at another version of the same output, we're going to focus in on the red box, or p-value, instead of comparing calculated t-statistic to critical values. We're now going to look at these p-values. This is the probability. If I'm looking at the actual variable of age, I'm looking at its p-value, interpreting that mess. 6.57 e to the negative 08 means 6, 5, 7, but I'm going to take the decimal place and move it 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. So it really looks like that. A very, very small probability. We normally draw a bell curve, and we have a critical value that's determined in part by alpha, usually 5%. This is a probability. A prescribed probability. But in the green, the printout also gives us a probability. A probability that's only going to take up a teeny tiny portion of the curve. It would be less than alpha. It would then be in the rejection region. But for shorthand purposes, we could just safely say if p is less than alpha, you have significance, and therefore you would reject the null. Let me try a specific example to make this a little clearer. Let's say that I have average temperature X and inches precipitation Y. And I want to know, does temperature help predict inches of precipitation? In the previous slide, in the blue, you see coefficients. These are called betas. Not mu's for mean, not rho's for correlation, but beta for coefficients. And I want to know, is the beta significant? It's not equal to 0, very similar to a correlation. It's not equal to 0, so it's significant, is my hypothesis. They would say it's not significant. It does equal 0. Well, let's assume in step 2 that alpha is 0.05. Instead of getting a chart value, we're looking at a printout value now. So we'll need our friend Excel. So we go to Data, Data Analysis, scroll down to Regression. Input Y first. That was our precipitation. Input X. And an output range. Here's my summary of everything. Again, I have a strong R, 0.859. That's a positive, a strong positive. An R square, I can say that 74% of precipitation is explained by temperature. So is it significant? I'm looking at the p-value of the x variable to find if it's significant. 0.000342023. The p-value from the printout, the first 3 digits were zeros. So when I compare them, I'm looking, is p less than alpha? P was 0.000. Is that less than alpha, 0.05? Yes, it is. What are we going to do? Reject. Reject the null. The null, that there is no relationship, is wrong. So our interpretation, there is a statistically significant relationship between temperature and inches of precipitation. Temperature helps predict precipitation. Once we know that we have a statistically significant relationship, we go back to the coefficients to make that prediction with y equals mx plus b. This being m, this being b. So first, my prediction equation, y equals mx plus b, m was 0.225, b was negative 15.42. Now if I ask you to make a prediction, if, say, the temperature x was 85 degrees, what would you predict by a trend line to be the y value? The predicted y would be 0.225 times 85 minus 15.42. Your predicted amount of precipitation, approximately 3.71 inches. Let's look at another example with class size, how many students, and the average score on a standardized test. We are hypothesizing that there is a relationship. We think you can use this variable for prediction, meaning it's not a 0. Zeros make things go away. We think there would be a coefficient. They would say, nope, it's 0. Alpha is 0.05. We need a p-value that comes from a printout. Let's go get Excel. Data, data analysis, regression, your y values, and then your x values, output range, and OK it. 0.977, that's a strong positive relationship between class size and score. R square of 0.955, so about 96% of score is explained by class size, but is it significant? The p-value, 2.77 e to the negative 5, moving your exponent into a decimal place, 5 places to the negative. That's the same as saying the two numbers shown in orange are the same. So when we go to test this for significance, we're going to take that value to 3 decimal places of 0.000 again, and compare them in step 4. Is p less than alpha? P was 0.000. Is that less than 0.05? Yes, it is. We will then reject the null. The null, again, is incorrect. We are correct, and there is a significant relationship between class size and score. Class size helps predict score. If there is a significant relationship, then I can use the x variable to help predict what will happen to the y variable. I've got to use the coefficients for this. So my prediction equation, based off of y equals mx plus b, will become y hat equals negative 1.04, because that's the slope. That's the amount that the y variable goes up, or in this case down, for every 1 point increase in the x variable, plus 103 for my intercept. So if I ask you to make a prediction, if the class size and I have to stay within the range, is 19, what would you predict the test score to be? Negative 1.04, multiply that by 19, and then add the intercept of 103.08. According to my rusty trusty calculator, I would predict on my trend line a score of 83.32 for anyone with a 19 in the population.